One interesting property of 2's complement integers is sign extension. Sign extension is an operation that has to be applied when a integer of a specific data types, which means a specific size, is moved to a larger data type with more bits available. So here in our example, I'm showing you an 8-bit value of -56. So if we'd like to extend this value into a larger data type, which occupies twice as many bits, what has to happen is that we take the original sign bit right here. So we take the original sign bit and we extend the sign bit into the higher bits. Interestingly, if you apply the rules to convert 2's complement number to figure out its magnitude and see if it's changed or not, this manipulation does not change the value of a negative number. Likewise, if we have a positive number, say 72, also starting with an 8-bit representation of 72, if we want to extend its value into 16-bit or a larger data type, what we must do is that we take the sign bit, this time 72 is positive, and we extend it into higher bits. Just simply paste this value of the sign bit into all higher bits when moving from smaller data type to a larger data type. And one very important note is that it's our responsibility, programmer's responsibility, to keep track of which values are signed or unsigned when we program values in low-level programming language in assembly. We have the responsibility to keep track of which values are signed and sign extend accordingly. If the values are unsigned, which means only positive numbers and 0, then of course we would just extend with 0 to the left to all the higher bits, regardless whether this bit is indicating 0 or 1. We just fill the higher bits with zeros in unsigned world because that doesn't change the value. But with 2's complement numbers, remember, sign extension is very important operation when you have to move from smaller data type to a larger size data type. We discussed the situation where overflow can occur due to the limitation of a specific data type. Arithmetic operations such as addition and subtraction could produce an overflow or underflow. Overflow is taking place when the current data type can no longer accommodate the result because the result becomes a larger size. We need extra bit to accommodate the result, for example. So when do we know that the overflow is taking place? Simply when both operands are positive and the result is negative, or when both operands are negative and the result is the opposite sign, which is positive. So when the resulting operation yields the opposite sign when we do the addition, in our case, in this analysis, this is indication of the overflow. When unsigned numbers, which means only positive numbers, are added, overflow is indicated by carry out of the leftmost bit. So essentially, clearly, to accommodate the full value, we need an extra bit, and therefore we just overflow the original data type. Next discussion here is about logical operations. Addition, negation, subtraction are arithmetic operations. So we also need to consider some logical operations before we actually start looking closer at arithmetic operations on bit patterns in computer memory. The logical meaning of 1 is true, and the logical meaning of 0 is false. So that's just a Boolean representation of true and false by using a single bit. Binary logical function AND is similar to addition and subtraction because it requires two operands, left and right, or A and B, just like addition and subtraction. However, the behavior of logical operation typically is described by the truth table. The truth table simply takes two inputs, reiterates all possible values of the two sides, 0, 0, 0, 1, 1, 0, and 1, 1, exhausting all of the possibilities right here, and assigns the result simply by providing its value. So you can observe that logical AND operation of 2 bits is yielding value 1 or true only when both of inputs are set to 1. In all other cases, we yield 0. OR operation is very similar, and its outcome is only when both inputs are 0, then the result of binary OR logical function is 0. If at least one of the inputs is set to 1, the result is 1. Unary function NOT simply flips the input. So it takes its unary value input, which is just a single input. So 0 becomes 1 and 1 becomes 0. It's also known as complement operation. So remember when we talked about 1's complement and 2's complement, parts of transition from negative to positive were flipping the values in the initial initial bit pattern, and so that operation is called complement. So complement operation gave names to these two representations. Another very popular operation which is available, another binary logical function, is exclusive OR. Once again, represented by truth table, and just to remember how it works, it yields 0 when both inputs are the same. So it tests the difference between the inputs, if you will. So if we have 0, 1, and 1, 0, which are not the same, they differ, the outcome of exclusive OR is 1. So this is yet another a binary logical function, which is very popular in cryptography and computing cryptographic hash values of data. Other logical operations that derive from bitwise manipulation and applying the logical functions that we already discussed is an idea of using binary masks. These masks are called bit masks, which apply that they're using bitwise manipulation of bits, and there's like one input and another input is a mask. So let's take a look at binary masks by example. Recall that we used a couple of inputs to compute addition of two binary values. So now I'm going to change this operation to an OR operation, for example. So the binary mask, so this should be recognized as a mask, and this is an input for the mask. So what we do is that we always compute the mask by simply comparing and applying operations to individual bits. Okay, so it's each bit is manipulated independently. For example, OR function yields 0 when only both inputs are 0. So in my case, what I have is that any situation where a 1 is present yields 1. So this is my outcome right here, all ones, because at least one presence of non-zero is everywhere in this example. Now we can try a different approach here to demonstrate another mask, or the same mask, but use the AND operation. So if you recall, AND operation yields 1 only when both inputs are 1, and I can see that right here I have two 1s, and so therefore this bit will be set to 1 as a result of applying this specific mask to my input, and all other bits will be set to 0 because I get 1 only in case when both inputs are 1. So you can see that masks using AND and OR operations are working on individual bits in multi-bit inputs. So the mask has to be the same size as an input, and then it's simply applying a specific operation, AND or OR, to an input, and we get the result accordingly. Floating point data type that represents real numbers with the floating point fractional values is going to be covered in our future courses, but for now I'm just giving you some links to explore the data type, the floating point data type, and some rules that apply to them. ASCII codes. ASCII stands for American Standard Code for Information Interchange. It simply is an encoding, the encoding schema of characters. And here in this table, I give you a quick look at decimal values, hexadecimal equivalents, popular names for characters that are considered to be control characters. Actually, control characters are all characters that are lower than decimal 32. So in range from 0 to 31, we have characters that are called control characters. Decimal 32 or hexadecimal 20 is a space character. Above that we have some punctuation characters, and above them we have digits, and so forth, including all alphabetical characters in this encoding. So recognizing ASCII character set is important because now it's a standard encoding for the initial part of international characters in HTML, and so this is something that we need to be able to practice with, to recognize the encodings and practice conversion from an encoding to a specific character. So once again, we'll address this in our laboratory exercise. Hexadecimal notation, which is presented in this table, is simplifying notation of bits. You can see that even 4-bit size binary values are quite difficult to deal with. It's just hard to spot specific patterns. They just all look alike in this entire column. So to simplify notation of large bit patterns, we use hexadecimal numbers. So hexadecimal numbers are corresponding to the decimal numbers in the range from 0 to 9. So in range from 0 to 9, the hexadecimal numbers are exactly the same. However, hexadecimal notation adds additional digits, which are A, B, C, D, E, and F, and F is representing 15, and A is representing 10, and you can see that together with 0 we have 16 values, which can be encoded by a single hexadecimal digit. So this helps us to encode bit patterns. For instance, once again, moving back to the examples that we've used in trying to compute our masks, you can see that the value such as 1010 can be written as a hexadecimal value. 1010 right here, so this would be hexadecimal digit A. So this is hexadecimal value A. Let's use a little X prefix right now. By the way, in C and C++, this would be 0x prefix to specify hexadecimal values. Likewise, if you look for the value represented by this bit pattern 0111 right here, this is in both decimal and hexadecimal is a 7. So this value would be written as 7, hexadecimal 7. As you can see, this notation would shorten quite a bit, replacing binary notation by, for example, if I try another example like this. So for instance, this bit pattern, I intentionally inserted spaces here to make it a little bit more readable, because otherwise it would be even more difficult to interpret. So now what I need to do is just look in this table and replace the actual values here by what the hexadecimal values would be. So this would be 7, 7. Let's look for a 1100 in this table. Right here, 1100 is a hexadecimal C. And this is recognizable 3. So this equals hexadecimal 77C3. Okay, so this hexadecimal notation is more popular, rather much more popular than the binary notation, because it effectively shortens the value. And most of the time when you're looking at the binary number, you probably want to either interpret it as a memory address, which could be anything. So therefore, whether you're using a binary notation or hexadecimal notation, it doesn't make much difference, but this is making it much more recognizable and a little bit more human friendly. So I have no plans to use hexadecimal notation for doing any computation. This is primarily just for mere convenience of replacing long bit patterns with hexadecimal equivalent.